Bismillahirrahmanirrahim. Assalamu alaikum everyone. My name is Abdul Saboor and I'm teaching the course of Introductory Electricity, and today is lecture number 12, and the topic of the lecture is electric flux and introduction to Gauss's law. The contents of the lecture are: first of all, we'll try to explain what is electric flux, what is area vector, what is the electric flux for a uniform electric field, and electric flux for a non-uniform electric field, and in the end, introduction to Gauss's law. Electric flux. According to definition, the electric flux is basically the rate of flow of the electric field through a given area, or we can say the amount of electric field lines passing through a flat surface with area A. So if you consider the definition, if you increase the number of electric field lines through a certain area, electric flux will increase. Electric flux is basically represented by phi and mathematically it is equal to the product of electric field and area A. So either you increase electric field or area of a certain surface or certain plane, your electric flux will increase. Its units is Newton meter square per coulomb. Now electric flux is basically a scalar quantity, which means it has no direction, only magnitude, and electric flux can be positive or negative. Now in order to understand electric flux further, we first try to explain area vector. What is meant by area vector? So according to definition, area vector is a vector of a plane surface whose magnitude is equal to area and direction is that of perpendicular to the plane. So according to definition, area vector has a magnitude equal to area and direction which is perpendicular to the plane of that surface. Now in order to further explain or understand this one, consider this square area in which we have side A and side B. So in order to find out the magnitude of this area, we have to multiply length into width and we'll get the area of this surface. Now if you want to find out the vector, area vector, the direction of this area, you have to take the cross product of length A and length B, and actually the angle between length A and B is 90 degree. So if we take the cross product, the direction will be always perpendicular to the surface of this plane. This can be easily explained by using right hand rule. If you consider the right hand rule and if you place your index finger on side A and your middle finger on side B, and the angle between side A and side B is 90 degree, so the direction will always be shown by the thumb, which is always perpendicular to both A and B, or we can say to the plane of the surface. Now electric flux for a uniform electric field. If you see in this slide, there are three equations. In the first equation, the total flux is basically the product of electric field and area A, and in the second equation the electric flux is equal to 0, which is minimum, and in third equation you have electric flux equal to E into cos of theta and into area A. Now these are three conditions and which explains the maximum, minimum and intermediate electric flux. In order to understand these equations, we should go towards some figures which explain these equations. Now, in first figure, you can see a uniform electric field passing through a certain surface. Now, you can see that the surface is perpendicular to the direction of the electric field, or you can say the area vector is parallel to the direction of the electric field lines. Now you can see that the number of electric lines passing through this area is maximum. So when the electric field line is up, passing into a certain area is maximum, then electric flux will be maximum, which is represented by mathematically electric flux is equal to E into A. In the second figure, you can see the surface of this plane is parallel to the electric field lines, or you can say the area vector is perpendicular to the direction of the electric field lines. So in this case, no field lines passes through this area, so the electric flux through this area would be equal to 0. Now in third case, you can see this surface is slightly tilted, or you can say the area vector makes a certain angle theta with the direction of the electric field lines. Now in order to find out the electric flux for this case, we resolve our electric field into two components. One is horizontal and one is perpendicular. The horizontal component is E cos of theta, and the horizontal component is E cos of theta, and the vertical component is E sin of theta. The vertical component is parallel to the surface, and the horizontal component is perpendicular to the surface, and the horizontal component of the electric field and the direction of an area vector are parallel to each other. So in this case, we can say the electric flux is due to the horizontal component of the electric field. So the electric flux will be equal to E cos of theta into area A. Now we can simply write the electric flux for a uniform electric field as the dot product between electric field lines or electric field and area vector A. And if we remove the dot, then we can easily write EA into cos of theta. Now if you can put different values of theta, so if we start with theta is equal to 0, the electric flux will be maximum, which means maximum number of electric field lines passes through a certain area. And if the theta is 90, that is the angle between area vector and electric field lines is 90 degree. So in this case, we have no electric field line passes through this certain area, and electric flux will be equal to 0. Now electric flux for a non-uniform electric field. Now if you consider the electric field is not uniform and the area is not flat, so what we do, we actually divide the entire area into small n area segments, such that delta A1, delta A2 and delta A3 up to delta AN, such that each area element is almost flat, and the electric field over each area element is considered to be uniform. In order to further understand this one, we will go to the next slide. If you consider this figure, you can see the electric field is not uniform, and the area is also not, or the surface is not flat. So we divide the whole surface into small area segments, such that this surface is flat of each area segment, and the electric field through that area segment is uniform. So we find the electric flux for each area segment, and then we add all the electric fluxes calculated from each of the area elements, and we add them up in order to calculate the total electric flux. Now the electric flux for the entire area is approximately written as it can be seen in this equation. The total electric flux is equal to phi1 plus phi2 plus phi3 up to phi n. Since the electric flux is a scalar quantity, so you can easily add it up. Now in the second equation, each of the electric flux is represented by their electric flux into dot product of area vector A. Now in third equation, you can see that you can sum all the electric fluxes from which runs from I is equal to 1 up to n, and if you apply the limit, you can replace the sign of summation into integration, and the total electric flux for the entire surface would be equal to integration E dot into small area dA. Now, introduction to Gauss's law. According to the definition, the Gauss's law tells us the total flux through a closed surface is always equal to 1 over epsilon naught times the total charge enclosed. In order to understand the Gauss's law, consider the following figure. If you can see in the figure, we have a spherical Gaussian surface, which is a closed surface, and we have placed a charge, a positive charge, at the center of the sphere. Since it's a positive charge, so the electric field will go outwards, radially outwards, and in order to find out the total electric flux, we first of all see what is the electric field and how we can calculate it. First of all, if you can see mathematically, the electric field is equal to kq divided by r square. We have previously done this. So if you replace the value of k into this equation, so the equation will become as q divided by 4 pi epsilon naught r square, where area of the spherical surface is 4 pi r square. So replacing 4 pi r square by area A, so the equation will become as E is equal to q divided by A into epsilon naught. If you take this area onto other side, so it will be multiplied with the electric field E, and the equation will become like this: EA is equal to q divided by epsilon naught. Since EA represents the electric flux, so replacing the left hand side with electric flux, so the final equation basically shows us that the electric flux is 1 over epsilon naught times the total charge enclosed. So inshallah, in next slides or in next lecture, we will discuss different aspects of the Gauss's law and different application of Gauss's law. So till then, assalamu alaikum.